Now I'm going to talk about properties of water. It's important to understand some basics of water chemistry in order to understand living systems. So we're going to go through some of the basic properties of water that make it the perfect medium for life. You can see obviously that most of the Earth's surface is covered in water. Your body as an adult is about 60% water, and there are some important properties of water that are very unique. I'm going to remind you about hydrogen bonds, because hydrogen bonding is going to be responsible for some of these unique properties of water. Remember, hydrogen bonds are what hold neighboring water molecules together. The two hydrogens and the one oxygen of a water molecule are held together by polar covalent bonds. But neighboring water molecules are connected by hydrogen bonding. These bonds are very weak, they're very transient, meaning this water molecule can be bouncing around and breaking and reattaching these hydrogen bonds between its neighbors. So we're going to start talking about the properties of water. The very first property that's very important about water is that water has what's called a high specific heat. And I'm going to define that for you, and then I'm going to explain why that's significant. So water has a high specific heat. This is really another way of saying water moderates temperature change. But chemically, what a specific heat means is it's the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius. You do not need to know that detailed definition. What you do need to know is that if a substance has a high specific heat, it means it takes a lot of heat input to increase the temperature of that substance. So this is saying it takes a lot of heat input to increase the temperature of water. Okay, conversely, water can lose a lot of heat before it decreases in temperature. So it takes a lot of heat input to get the temperature to go up, and it can lose a lot of heat before the temperature goes down. In other words, water moderates temperature change. Why is that a big deal in living systems? Well, just on a very basic level, if you look at that fish, the reason he's saying he loves the specific heat capacity of water is because if you live in an aquatic environment, your temperature day to night and season to season isn't going to change a whole lot. You live in an environment with a pretty constant temperature. And that means you don't have to really moderate your internal temperature. You don't have to metabolically regulate your body temperature because your surrounding environment has a pretty constant temperature. When animals moved onto land, this was one of the biggest problems they faced because, as you know, on land, season to season and day to night, there's a big temperature variation. So water moderates temperature change, and this applies to aquatic organisms, which most life on Earth is in the oceans. The other consequence of this is just weather. We know that if you live near the coast, it is much cooler during the day than if you live in the desert. This shows San Diego at 72 on the same day that Palm Springs is 106. That's 34 degrees difference. Also, day to night and season to season, there is much more of a difference inland than if you live in a coastal area. And that's because water moderates temperature change. As far as we're concerned, though, obviously we're not aquatic organisms. Obviously, yeah, this affects us, but isn't going to make or break us. The big deal for us is that chemical reactions in the body release heat. When When you break down your food molecules, it releases heat. Lots of chemical reactions in the body release heat. If you had another liquid in your body, you would burn up pretty quickly. The fact that water moderates temperature change is a really big deal in living systems. All that metabolic heat is absorbed before water increases in temperature. The reason for that? The hydrogen bonds. Hydrogen bonds are responsible for this property of water. Those hydrogen bonds can absorb a lot of heat before water increases in temperature. And that's the reason water is able to moderate temperature change. So this is a big deal. Related to this property of water, a very similar property, I'll give it a number 2 on the numbering of properties of water, but it's really very related. And that is that water has a high heat of vaporization. What does that mean? That means it takes a lot of energy input before water turns from liquid to vapor. If you had alcohol coming out of your pores instead of water, this would not be the case. So what happens is we sweat, and that water stays on the skin rather than just instantly vaporizing and evaporating. It stays on the skin and it cools the body. That's called evaporative cooling. This is a very important part of maintaining our body temperature and regulating our body temperature. Keeps us from overheating. If you do go out and drink too much one night and you decide the next morning you're going to go for a run, one of the ways our body rids itself of toxins is through the pores of your skin and through sweating. So if you have alcohol coming out of your pores, you're probably going to overheat faster. You're interfering with this process. So again, this is very related to water moderating temperature change. Okay, third property of water. The next 2 are kind of related to each other as well. Cohesion and adhesion. So 3 is going to be cohesion, and 4 is going to be adhesion, and I'll explain the difference. Cohesion is water molecules sticking to each other, and adhesion, excuse me, adhesion is water molecules sticking to other molecules. Okay, so cohesion, water molecules stick to each other. You can see that in this picture, the surface tension on this water. You can see under that little water strider's legs. The water molecules stick together and they're constantly pulling on each other. And they create this surface where a water strider can actually walk on top of the water. You can actually feel that surface tension in that picture. So that's kind of cool, but maybe you don't care so much about that. But it's what really creates water droplets. When it rains, that's because of cohesion. The way the water comes out of the sky in droplets, that's because of cohesion. So, very small right here, water droplets. I'm sorry, I have this tickle in my throat. Okay, adhesion is water molecules stick to other molecules and to surfaces. So water molecules stick to other molecules, okay, and surfaces. If you've ever put your finger on the end of a straw and pulled water up a straw, you know about adhesion. If you've looked at a glass of water and you realize that the water in the glass doesn't go straight across, is because it's being pulled up on the sides of the glass. That's adhesion. Who cares about that? Well, we care about that for a couple of reasons. One, that's how plants are going to move water hundreds of feet into the sky. It's not really moving into the sky, but it's going from the roots down in the soil where the water is. A tree can move water all the way up to leaves 100 feet in the air or more. And it does this because of adhesion, because water can be pulled up a tube. Okay, so that's pretty cool. We need plants. But what about us? What vascular system do we have that we need to move fluids through? Our blood vessels. Similar story. So plants and animals need to move fluids around through their tissues. So this is a very important property of water. Squeaky marker. Okay, and then property number 5. Ice floats. More technically, solid water is less dense than liquid water. That's pretty crazy in the chemical world. If I melted some aluminum in a beaker, put it on this table, and I dropped in a piece of solid aluminum, do you think it's going to float? No, it's going to sink right to the bottom. Solid aluminum is much more dense than liquid aluminum, and that is the case most of the time. The fact that ice floats is a very strange and unique phenomenon in chemistry. Solid water is less dense than liquid water. The reason for that has to do with hydrogen bonding again. You can see that when water freezes, those hydrogen bonds are no longer breaking and reforming, and it keeps these water molecules at a fixed distance, and it kind of has this rafting effect where ice floats. Why do we care about that? Well, again, most living organisms are in aquatic environments. And if you're living in an aquatic environment and winter starts coming, if solid water was more dense than liquid water, this aquatic environment would start freezing from the bottom and keep freezing and keep freezing. And before you know it, Mr. Fishy is in a solid block of ice. Not a good plan. Instead, ice floats. So not only is Mr. Fishy not going to be in a solid block of ice, but now this is going to create a thermal blanket. And now when the air gets really cold, that water temperature is going to stay fairly constant. It's going to insulate the water. So that's pretty cool if you're a fish or any other aquatic organism. Okay, so these are the properties we've talked about so far. I broke cohesion and adhesion into 2 different ones. So water has a high specific heat. It has a high heat of vaporization. Water molecules stick to each other and to other molecules through hydrogen bonding. And solid water is less dense. All of those properties are due to hydrogen bonding. So quick question. Breaking down starch into glucose releases heat. What property of water explains why our cells don't overheat? What is it about water that moderates temperature change? Well, technically it is that water has a high specific heat. You can add a lot of heat before water increases in temperature. What property of water allows plants to move water from their roots to their leaves? So remember 2 properties. One is water sticking to water, and then the other is water sticking to other surfaces. So it would be adhesion. These are the properties of water we've covered so far. Water has a high specific heat and a high heat of vaporization. both due to hydrogen bonding, both regulate temperature change. Cohesion and adhesion, water sticks to other water, water sticks to other molecules due to hydrogen bonding. And then finally, ice floats due to hydrogen bonding. Now we're going to move to the next property of water. And that is water is an excellent solvent. I think we're on number 6 on our list, because I broke cohesion and adhesion into 2 different numbers previously. So water is an excellent solvent. What is a solvent? Well, in order to define a solvent, I need to define solution. A solution, which we're just one big old bag of solution, a solution is a solute plus a solvent. So here's our word solvent. Solute is what's dissolved in the liquid, and then the solvent is the liquid. So liquid is the solvent, okay, and the solute is what's dissolved in the liquid. And that makes a solution. There's an important term to describe the strength of this solute. So you know you can have water that's really, really salty, or you can have water that's just a little bit salty. You can have water that's a lot sugary or just a little bit sugary. Obviously, if you have a fixed volume, so say you had a 1 liter solution, okay, and in this one, we're going to put 100 grams of sodium chloride, and in this one, we're going to put 1 gram of sodium chloride. Even though these are both a 1 liter solution, this one obviously is not going to be nearly as salty as this one. And the way we express the strength of that solute, okay, so sodium chloride is our solute. The way we express the strength of that is we use a term molarity. Molarity is how we're going to express the strength of a solute in the solution. This is going to be important when we talk about how water moves across cell membranes, in and out of a cell. And solute concentration is going to help determine that. We use these units. M, capital M with a line under it, stands for moles or molar. If we had a 10 molar sodium chloride solution and a 1 molar sodium chloride solution, that 10 molar solution is going to be 10 times stronger than the 1 molar. And you're going to probably learn, if you're taking the lab for this course, you're going to learn how to calculate molarity and learn how much salt you would have to add to get a 10 molar solution versus a 1 molar solution. It's not 100 grams. This is a different example. But molarity is how we're going to express the strength of a solute, what's dissolved in the water. Okay, so water is an excellent solvent. Lots of things dissolve well in water. What dissolves in water? What kinds of molecules dissolve in water? Another word for dissolve is dissociate. So what dissociates or breaks apart in water? If things come together, it's associate. If they break apart, it's dissociate. Does water mix with everything? Does oil mix with water? Do different fuels mix with water? No. So what dissolves in water? Well, 2 categories of things that dissolve in water. Polar molecules and ions dissolve in water. Non-polar molecules not dissolve in water. The way you can remember this is polar bears love water. If something's polar, it loves water. Another term for water loving is hydrophilic. Philos means love. Hydro obviously means water. Hydrophilic, water loving. Polar molecules are water loving. Nonpolar molecules are actually repelled by water. And they're called hydrophobic, water-fearing. If you have a phobia, you're afraid of something. These are the water-fearing. They're actually repelled by water. So sometimes it's the entire molecule that's either hydrophobic or hydrophilic. Sometimes it's a portion of the molecule. Sometimes you can have a molecule that is hydrophobic in one region and hydrophilic in another. And we're going to see that example in a couple of minutes. So if we look at this sodium chloride, it breaks back down into ions when it's mixed with water. It readily dissociates in water. Water actually forms what's called a hydration shell around the solute. It surrounds that ion and keeps that sodium and that chlorine from coming back together. We all know that if we put this beaker out in the sun and the water evaporated, that salt would still be left in the bottom. It would come back together when the water is gone. But water is an excellent solvent. It's a great solvent to be in a living system. It doesn't compete with a lot of different things. It just allows the chemistry to happen. Okay. Water organizes nonpolar molecules. This is a very important seventh characteristic of water. Okay, so I'm going to keep the board up there that's telling us what's polar and what's nonpolar. So it's the polar molecules that are going to dissolve in the water and become a solution. What happens to the nonpolar molecules? Well, sometimes water helps shape them, helps organize them. And I'll explain that. So number 7, water shapes or organizes nonpolar molecules. So if you're nonpolar, are you water-loving or water-fearing? You're water-fearing. You're repelled by water if you're nonpolar. We have some very important molecules called phospholipids that make up the membranes of our cell. So your cell has a nucleus that's surrounded, defined by a nuclear envelope. It has a plasma membrane on the outside. It has a whole lot of membrane-bound organelles that you'll learn about. Every single one of those membranes is comprised of phospholipids. And phospholipids, in their cartoon form, have a phosphate head. You'll learn what a phosphate group is in the next unit when we talk about organic chemistry. And that phosphate head is actually hydrophilic, water-loving. It's polar. And then we have 2 tails that are just made primarily of carbon and hydrogen. They're hydrocarbon tails. And hydrocarbons are just like fuels. If something's called a hydrocarbon, it means it's just made of hydrogen and carbon. And those hydrocarbon tails are nonpolar. hydrophobic, water-fearing. So what happens when these phospholipids come in contact with water? Well, the tails are going to turn away from the water, and the heads are going to interface with the water. So let's go back to the previous example. It's a little more basic. Okay, so we have polar head, nonpolar tail, and when they come in contact with water, all those tails are going to turn inward, and all the heads are going to be on the outside, and it's going to form this sphere. It's going to form a sphere where all the water-loving heads are on the outside, and all those water-fearing tails are going to point inward. That's called a mycele. It's a sphere of phospholipids. This is actually how soap works. So, used to be that Pa would go out and kill a critter, and you would take that fat and you would make soap out of it. And then you would eat the meat the whole year, and you would make clothes out of the hide. Now, we realize pork fat doesn't smell as good as vegetable fat, so we use things like lavender now for our soap. But nevertheless, it's still phospholipids, and when it contacts water, it's going to form this mycele, and it's going to trap dirt, and you're going to rinse it away. So that's it. There's just water on the outside. But in our cell, going back to here, oh, I already drew cell. I need to draw one again. We have water in here and water out here. So what happens then? Well, now what's going to happen, you already saw, that is, it's going to form what's called a phospholipid bilayer. Phospholipid bilayer. You're going to hear that a lot in the next few weeks. When we get to the cell and cell membranes, you're going to hear phospholipid bilayer a lot. So water on the outside, water on the inside. Heads, heads, all the tails point inward. So if you imagine that along the whole surface of your cell, heads pointing toward the water, and all the little water-fearing tails pointing in. And that's called a phospholipid bilayer. 2 layers of phospholipids. Phospholipids have a phosphate group with lipid tails. Very, very important. Water forces this shape. Water causes membranes to have this shape. Water causes phospholipids to have this orientation. That's very important to understand. So what is another term for polar molecules? Polar. Polar bears love water. So water-loving, hydrophilic. Okay, we have one more important property of water to discuss. And this one is a little more involved. So this will be number 8 on your list. And that is that water dissociates into ions. We're not going to spend a ton of time getting into the details of the chemistry, but what this relates to is acid-base chemistry. And that is a very important component of living systems. Your body constantly tries to keep pH constant. Why? Because any subtle change in pH in your body is going to denature proteins, namely the enzymes that carry out all the important chemical reactions in your body. So keeping pH constant in the body is very, very important. So it's important to understand acid-base chemistry. And that is based on this fact that water dissociates, in other words, breaks apart into ions. You remember what ions are? They are not atoms. Atoms don't have an electrical charge, but these are going to have a net charge. In the most simple form, some textbooks really just give you the simple version of this equation, and that is water breaking into hydrogen ions and what are called hydroxide ions. So hydrogen ions and hydroxide ions. Hydrogen ions, when they're free in a solution, are going to make the solution acidic. This is what makes something an acid. Hydroxide ions in a solution are going to make something a base. When these two are equal, it's what we call a neutral solution. These little brackets mean concentration of. So when the concentration of hydrogen ions is equal to the concentration of hydroxide ions, that's what we call a neutral solution. And we assign that a pH value of 7. That's what we consider neutral pH on the pH scale. pH, it's always little p, big H, because it stands for potential hydrogen. And hydrogen is capitalized just like California is. This is what makes something an acid. So when it's greater, then the solution is an acid, which means it's below pH 7. Anything below pH 7.0 is an acid. When it's the other way around, remember the mouth is always eating whatever's bigger on the greater and less than sign. Okay, so when this is bigger, the hydroxide ion, that's what makes it a base. And that's above pH 7. So anything above pH 7 is a base, and anything below pH 7 is an acid. The scale goes to 14. So this is the pH scale. 0 to 14. Sometimes you see it flip the other way. I actually kind of like it flip the other way with 14 at the top. Okay, but an acid has a greater hydrogen ion concentration. When they're equal, it's neutral. When the hydroxide ion concentration is greater, it's a base. Just looking at some common things that you should probably know whether they're an acid or a base. Human blood is a little bit basic. It's about 7.3 to 7.4. Seawater is basic. Bleach is a very strong base. Drain cleaner is a very strong base. People think that stuff you pour down the drain to eat clogs is an acid, but it's actually usually a very strong base. And in fact, when you spill bleach on your hands and your skin feels slippery, that's that very strong base eating your skin off. So a strong base is very dangerous too. Digestive enzymes, between pH 1 and pH 2, just depending. Coca-Cola has an acidity very similar to stomach acid. You can pour it on a piece of meat and it will digest it. So just some examples of common acids and bases. Coffee's a little bit acidic also. Urine's slightly acidic. So the body needs to keep pH constant. Why does it need to keep pH constant? It needs to keep pH constant because we don't want to denature our proteins. So in the next lecture, I'm going to talk to you about what it means to denature a protein, why that's bad in the world of enzymes, and what the body does to prevent that from happening. We're going to talk about buffer systems.